Welcome to our lecture on energy transition. Today we will talk about fluctuating renewable energies, in particular solar energy. Today we will talk about solar radiance. The next lectures we will talk about solar thermal application, solar concentration, and then photovoltaic systems. Then go to wind power, then with energy with constant output, that is hydropower, geothermal energy, and biomass power. Later on, we will talk about energy storage technologies and then perspectives and feasibility of energy transition. At the end, I will talk about simulation tools such as Homer, PV-Syst, and Meteor Norm. The excursion due to the coronavirus will not take place. Let's start with the major source of energy. We have here energy from the sun. The sun is quite far away from planet Earth. It's about 150 million kilometers away. So this picture in the middle, in the center, is not representative. We will see later a real picture of that. The energy source is a nuclear fusion that takes place at a temperature of about 15 million degrees Kelvin. And the surface of the sun is relatively cool, about 5,800 Kelvin, and that's the part we are seeing. Interestingly, that's comparable to the inner core of the planet Earth. It's about the same temperature, 5,800 Kelvin. The spectrum of this black body temperature you see in the top right. This is a spectral distribution of the sun. This was discovered by a physicist named Planck more than 150 years ago. You see the visible part of sunlight or sun irradiance going from 400 nanometers to 800 nanometers. More than 800 nanometers is called infrared radiation. On the left part, for lower wavelength than 400 nanometers, it's called ultraviolet. The power that is reaching the Earth is quite high. It's 178 petawatt. It's more than 10,000 times we consume. This is a real representation of the sizes of the sun and planet Earth. So you see that the sun is much bigger than our planet. And the next you see the real distance. So here it's a bit shrunken, and you see here on the left part the sun and almost invisible the planet Earth, and that's the real, not the real distance, but a representative distance. This is not representative, but it explains quite well the situation we have here. The axis of the rotation around the sun is not in parallel with the auto-rotation axis of Earth. This was due to an impact that happened a long time ago and created our moon. And due to this impact, we have a deviation of 23.5 degrees from parallel. This leads to our seasons. So in 21st of June, the northern hemisphere is more tilted towards the sun. And if we go on to the 21st of December, the southern hemisphere of our planet is more towards tilted to our sun, so it receives more sunlight. There are two other specific dates, the 21st of March. During this date, the sun is sitting perpendicularly on the equator, and northern and southern hemisphere receive the same amount of sun irradiance. And also the duration of day and night is for all parts of the world 12 hours day and 12 hours night. The same occurs also for the 22nd of December, and there you have the same situation. So we have 12-hour daylight and 12-hour night. The value of the irradiance above the atmosphere is 1667 watt per square meter. This is the irradiance what the satellites directly above Earth receive. If you go down to Earth, we will talk a little bit later about that, you receive in the vicinity of a maximum 1000 watt per square meter. While this occurs above the atmosphere and is relatively constant, we call it also solar constant, E index 0. This is the perspective from an observer on the Earth. So we have the sun with a certain deviation from north or south. This is called the solar azimuth, alpha index S. And we see the sun at a certain height. This is called the sun elevation, gamma S. There are in literature, there are some differences. Some people say we take the deviation from south only, so if the azimuth measured from south. Some people prefer the expression zenith angle, so they measure the angle between the sun and the zenith. We take the expression which is fixed in the German industry norm standard, and so we take the azimuth deviating from north and the elevation angle, not the solar zenith angle. These are some examples in the case of Berlin. So we never reach perpendicular irradiance in Berlin. The highest the sun gets is at an angle of 60.8 degrees of elevation angle. This occurs at the 21st of June. The lowest angle that occurs is on the 21st or 22nd of December, and it's 14.1 degrees only. It's all during midday. If you consider Paderborn is a little bit more south of Berlin, so we have to consider the latitude angle between Berlin and Paderborn, which is 0.6 degrees. So that means in winter, 21st of December or 22nd of December, the elevation angle of the sun in Paderborn is 14.7 degrees. Also, you have to add 0.6 degrees for all the other angles, for example, 21st of June, so it's 61.4 degrees then. We have an expression here called AM, air mass. I will explain in the following. So this is a path of the sun during daytime at different parts of the year. So if you take the lowest curve, you have here the solar azimuth, 180 degrees. That means this is 180 degrees from north, so it's the southern direction. The elevation angle, as you know, for lowest position at the midday is 14.1 degree in Berlin at the 21st or 22nd of December. And we have the sun goes up at solar time at 8 a.m. and goes down at 4 p.m. If we take the other extreme at the 21st of June, sun already goes up at solar time 4 a.m. or even before 4 a.m. and goes down at about 20:30 or 8:30 p.m. So there's a considerable difference in day duration. Germany, this is not always the case. We will take a look at a second example. You see that's not always the case. This is the second example. This is Cairo. It's located at a latitude of 30.1 degrees north in comparison to Berlin, which is more than 52 degrees north. And the sun is still not perpendicular, but almost perpendicular. So the maximum elevation angle in Cairo is 83.4 degrees. And this is also called AM 1.01. Same as the 21st of June, and the lowest position on 22nd or 21st of December. This depends which year you have. We have sometimes switching year. This is due to the duration of the year, which is 265.25 days. So that's not exact number. Therefore, this is changing sometimes. So the lowest position we have in Cairo is 36.6 degrees of elevation angle gamma S, and the highest angle, as I mentioned already, 83.4 degrees. Here you see also the path of the sun in Cairo. As you see here, lowest position is quite high. As you see here also, the sun rise doesn't deviate too much during the year. So the longest day of the year, it's about 5 a.m. The sun goes up at 5 a.m. and goes down at 7 p.m. At the worst day of the year, it goes up at about 6:30 a.m. and goes down at about, how much is that here? about 5:30 p.m. So this deviation during the year is much less. This is another extreme. It's Rio de Janeiro, which isn't directly on the equator, but 23.5 degrees south of that. So the seasons are exchanged. So we have the highest position of the sun at the 21st or 22nd of December and the lowest position of the sun at the 21st or 22nd of June. So I mentioned already the air mass. The air mass describes the path length of solar radiation through the atmosphere. The shortest is perpendicular irradiance, so we call this air mass 1. For the satellites, as I mentioned already, we have air mass 0, so it's also called solar constant. If we go to another position where the sun has a different angle than perpendicular, the path length is increasing. In this example, we have an air mass of 1.5, which is also used as a standard for measuring the efficiency, for example, of solar photovoltaic devices. And this is at an angle of about 42 degrees. This is called AM 1.5. The irradiance is attuned to 844 watt per square meters, while if you go above the atmosphere, as I already mentioned, the level of irradiance is 1353 watt per square meter. This is the definition of the air mass. So this AMX is 1 divided by the sinoid of the elevation angle gamma s. So you see here AM1, the elevation angle is exactly 90 degrees. So 1 divided by sinoid of 90 degrees is 1. Therefore, this is AM1. If you go to another angle, for example, 42 degrees, then 1 divided by the sinoid of 42 degrees, we have 1.5 as air mass. Here you see the effect on the spectrum. So first we started with the black body radiation, 5800 or 6000 Kelvin black body radiation. So that's the surface of the sun. Then even at this last distance of 150 million kilometers, the spectrum doesn't change a lot. So we have the AM0 radiation just directly above atmosphere, and through the atmosphere it's attuned. So you see that the blue part at shorter wavelengths is heavily modified. Due to the absorption of the sun, we have a significant reduction of irradiance, especially at the low wavelengths. The ultraviolet part is drastically reduced, but also on the visible and especially on the infrared part. Here you see the spectra due to the different elevation angles of the sun during different parts of the day. So this is a location at the equator at equinox. That means 21st of March or 22nd of September. We start at midday. At midday at the equator at equinox, the irradiance comes in perpendicularly. So we have AM 1.0. So this you see above here. And you have the full spectrum. And if you wait for 1 hour and 20 minutes, we have an elevation angle of 70 degrees with an air mass of 1.06. You see already that the peak is already reduced and some part of the blue spectrum is reduced. If you wait further on, for example, to 4 p.m., 4 hours after midday, we have already AM2 at an elevation angle of 30 degrees, and we see here the drastic reduction of the intensity of solar radiance, but also a change in spectrum. So here the blue and ultraviolet part is heavily reduced, but also here some bands which are reduced. And if you go just before sunset at 5:20 p.m., so at equinox, at these days we have exactly at 6 p.m. the sunset, so 40 minutes before sunset at an elevation angle of 10 degrees or AM 5.76. We have a very red spectrum. The blue part doesn't exist anymore. You see here, focus here is on the red part in the vicinity of 700-800 nanometers. Therefore, the sun at this elevation angle appears to us as reddish. This was direct irradiance, but we also have a lot of diffuse irradiance. Not all part that goes through the atmosphere is absorbed. Some is scattered only. This is a diffuse irradiance. Did you see at the blue sky? We observed already that basically the blue part is heavily absorbed or scattered, and therefore a large part remains in the atmosphere and is scattered at different angles. This is called the diffuse irradiance, and this is the reason why the sky appears blue. This is so-called the Rayleigh scattering. So this is our absorption point. So we have a receiver surface. So the first part we talked about was direct irradiance, but we also receive a large part diffuse irradiance. In Germany, it's almost half of the irradiance comes in as diffuse irradiance. In other countries, even with a very clear sky, 20 to 30% are still diffuse irradiance. Depending on the ground and the reflectivity of the ground, we have also a thing called albedo. So this is a reflection of the incoming irradiance from the ground onto our receiver surface. The so-called global irradiance consists of direct diffuse irradiance plus albedo. To give you some quick estimations of the irradiance levels, so if you have clear sky on the right side here, it's a maximum in Germany 1000 watt per square meter if you have a very, very clear sky in the summer at midday. If you're not in summer and you still have a very clear sky and a lot of irradiance, it's in the vicinity of 700 to 800 watt per square meter. If there are some light clouds, the irradiance is in the vicinity from 200 to 700 watt per square meter. At really clouded sky, the irradiance can go down to 50 watt per square meter. If it's lightly clouded, to 200 watt per square meter. This is for other location, Brazil, compared to Germany, to Hamburg. So the black line is Hamburg. This is daily irradiance in kilowatt hour per square meter per day. So you see in summer in Hamburg even it's not bad. So we have about 4 kilowatt hours per square meter per day. If you go down to winter, it's below 1, or even if you go to December, it's in the vicinity of 0.5 kilowatt hours per square meter per day. This is compared now to Brazil, as I already mentioned. Here, for example, Rio de Janeiro, the bold red line here, you see that winter and summer are exchanged to Germany. So we have winter in June, so with the lowest irradiance, but it's in the vicinity of the highest irradiance in Germany, in the vicinity of 4 kilowatt hour per square meter per day. The highest irradiance in Rio de Janeiro is in summer, then February, January or December, and this is in the vicinity of about 6 kilowatt hour per square meter. These are some other locations in Brazil. For example, the most southern point is Porto Alegre, 30 degrees south of the equator. You see here that in winter the irradiance goes down to 3 kilowatt hours per square meter per day. In summer it's about the same as Rio de Janeiro. This is now Berlin. This is the yearly irradiance, not per day, per year, in units kilowatt hour per square meter per year. If you have the azimuth, this is now from literature which considers south as azimuth 0, not 180 degrees as according to the industry norm. If you position your receiver looking south at an elevation angle here of the receiver of 30 degrees, we receive 1100 kilowatt hours per square meter per year in Berlin. If you modify it, for example, if you have a steeper angle than 30 degrees, for example, going up to 60 degrees, then you have a reduction, but it's not really that much. So it's about 10-20% reduction of solar irradiance. If you consider a facade, south-facing facade, you have a loss in the vicinity of 30-35% compared to the optimal orientation of your receiver. If you deviate from south, you see that if you go in angular deviation plus minus 10 degrees. There is not much change. If you go further, even then the change is not really big. Here is the accumulated irradiance during a year all over Europe. Get some data here from Berlin. So you saw here about 1000 kilowatt hour per square meter per year. In Paderborn it's a bit less, so a bit darker green color, in the vicinity of 950 kilowatt hours per square meter per year. Here you see Spain as an example, here Seville. You see here irradiance goes up to almost 2000 kilowatt hour per square meter per year, or Sicily or Crete and so on. But altogether, if you see it later for wind power, the difference is not really that much. It's just a factor of 2 between the best and the worst location in Europe. If you go outside of Europe, for example, here South Africa, the irradiance can be higher. This is, for example, if you take a look at Johannesburg, the one you see here, global irradiance level in the vicinity of 2,400 to even 2,600 kilowatt hour per square meter per year. This map is already translating it to solar electricity to be generated. So if you install a photovoltaic generator with a peak power of 1 kilowatt peak, you will generate here, for this example, 2,400 kilowatt hours per square meter per year in the vicinity of 1,800 kilowatt hour of electricity. You have also maps for the year or simulations programs. This is taken from the Swiss program Meteornorm. You see here we have in Europe, as I mentioned, best point in Europe is about 2,000 kilowatt hour per square meter per year. We saw Johannesburg 2,500, 2,600 kilowatt hour per square meter. Comparable here to northeast Brazil or to Chile and Bolivia or Mexico and the southern part of the United States or Australia. How you measure solar irradiance? This instrument is called pyranometer. So it measures solar irradiance by absorbing solar irradiance on a black plate. The sunlight passes through these domes, which are highly transparent, and then gets absorbed by this plate. This plate heats up, then you have a reference element against it, and you have a temperature difference between these two plates. And this temperature difference you measure by using a Seebeck element or a thermopile. This gives some output of some millivolts. And if the pyranometer is well designed, this Seebeck voltage or thermopile voltage is proportional to the solar irradiance. These domes avoid the cooling of the plate by wind or by convection. The other method to measure solar irradiance is a silicon sensor. You use a photovoltaic effect, and the photovoltaic effect transforms photons into electrons, and therefore solar irradiance is directly proportional to the current or the electron flow. And if you put a shunt resistor here, you have a voltage that is proportional to the current and the irradiance then. What you have to consider, the advantage of the pyranometer is that it absorbs any kind of irradiance. So if the domes are highly transparent for all wavelengths, the absorber also absorbs any wavelength. You have the full spectrum considered there. This is not the case for the silicon sensor because there's a spectral sensitivity. We talk about it later when we talk about the photovoltaic effect. So it doesn't value all wavelengths the same way. This is a construction actually which has 3 pyranometers but in different configuration. On the left part you see here the measurement of the global irradiance. So it absorbs irradiance coming from all different parts, either direct or diffuse irradiance or even albedo irradiance. On the right part you see a pyranometer, but this is shadowed by a so-called shadow board. The shadow board is positioned in such a way so it stands directly in the path between the sun and the pyranometer. So it's causing a shadow here on the pyranometer. By this construction, you measure the diffuse irradiance only, and the diffuse and the albedo irradiance only. Here, this tube is the absolute opposite. It's directly positioned towards the sun, orientated towards the sun, and you measure direct irradiance only by that. This is our data acquisition system on the rooftop of the University of Paderborn. So we have here a global pyranometer. We have here, call it solar hedgehog. So it measures solar irradiance in all different directions. And we have here a meter for measuring precipitation and the wind speed and wind direction. Here we have solar modules. This is a quite old picture. Nowadays it's all covered with solar modules here. This is a monthly irradiance at some locations. So we have here the situation in Seville in Spain. So we have here, if you consider a horizontal irradiance, we have a 78 kilowatt hour per square meter in January, and the best is 218 kilowatt hour per square meter per month in June. If you elevate the receiver a little bit, then the situation gets drastically better in January. So we have here 30 to 40% more of irradiance because the elevated plane is more looking towards the sun. We have a little bit reduction in summer, but that's only about 10%. And the most important thing is solar energy is also scarce there in January, that you have here a higher irradiance level there. If you add all up the different months here, if you have a horizontal irradiance only, you end up at 1,700 kilowatt hour per square meter per year. If you have an inclined plane at 30 degrees of module elevation angle, here gamma m is equal to 30 degrees, we almost come to 2,000 kilowatt hour per square meter per year, or exactly 1,944 kilowatt hour per square meter per year. So an example, solar irradiance in Paderborn. So this is a horizontal, and these are daily irradiance levels. So here this is monthly irradiance level, and this is now daily irradiance levels in watt hour per square meter. So in January we have in the vicinity of 0.596 or 0.6 kilowatt hour per square meter for a horizontal measurement system. If you incline it optimally, this is a very steep elevation angle, it's 65 degrees, we get considerably more irradiance, 0.97 kilowatt hour per square meter per day. If you take a look at the June values, so we have for horizontal irradiance, we have 5.3 kilowatt hours per square meter per day. Optimal inclined, it's even less. Then we have here 5,190 kilowatt hour per square meter. In average, we have over the year for horizontal irradiance, average daily, we have 2.8 kilowatt hours per square meter per day. And for the optimal inclined surface, we have 3.2 kilowatt hours per square meter per day. What often is chosen for different constructions an elevation angle of 30 degrees, and there we have almost the optimum here, 3.2 kilowatt hours per square meter per day in average. And here the optimum would be here 36 degrees, so we don't deviate so much if we select an elevation angle of our receiver of 30 degrees. This is now for Namibia in the southern part of Africa. So we have here much higher irradiance levels. Also, the difference between summer and winter is much less. Don't forget, it's on the southern hemisphere. So we have summer in January. Their irradiance goes up to 7 kilowatt hour per square meter per day. And lowest is in June, July, which is in the vicinity of 4.75 kilowatt hour per square meter per day. In average, we have about 6.35 kilowatt hour per square meter per day for horizontal irradiance, and the optimal inclination angle isn't too far from that. It is a 6.88 a kilowatt hour per square meter per day. If we choose an elevation angle of 30 degrees, we are also not so far from that. The optimal elevation angle would be a bit flatter than in Germany, in the vicinity of 25 degrees gamma m. Also, you have to consider the adequate distance between the rows of different solar collectors, not considering only one single receiver. You have always rows of receivers for a big power plant. And then you have the height. The height gets higher as you increase the elevation angle of your receiver. And rule over the thumb in Germany says just to have a good compromise between area use and losses by shadowing, that you choose a distance which is in the vicinity of 4 to 6 times the height. So you can also calculate this on your own. So you have here the module elevation angle, or it's called here E with the receiver as a receiver angle gamma E. Then you have the height here. This is a distance between the two. Then you have here the position of the sun. And there's exactly no shadowing if sun is in that position. So if this high, so it's exactly right. There is no shadowing. If the sun is a bit lower, for example here, then you cause a big shadow. In this case, the shadow covers half of the area of the PV module. Here you divide this distance d into d1 and d2 here. So d1 is between the perpendicular on the surface going to the top end of the module, and d2 is from that towards the lower end of the second module row. If you put in the numbers, it's also be part of the exercise, sometimes it's even part of the tests at the end. Then you have here d is d1 plus d2. d1 here, this part is the cosine of the elevation angle of your receiver, and d2 is here the h divided by tangents of alpha, the sun elevation angle here for not causing a shadow, and this is then L multiplied by L for sure, yes, because it's a module length here, for example 1 meter, or newer models have 2 meters. And this stays the same, and you can also substitute this part by sinoid of gamma E divided by tangents of alpha. Or you can use the Pythagoras, so you say here d is d1 plus d2, and this is rectangular triangle here, and then you have here for d1 is L square, which is the hypotenuse, minus h square, and you take the square root out of it, and this is the same as here. Then you come to that formula. You can show here that this is equal to that. This is some pre-calculated examples here. So you have this is shadowing angle of the sun. So remember, for the lowest position in Berlin in winter, we have a sun elevation angle at midday of 14.1 degrees. So this is in this vicinity. And this is the module elevation angle. Typical value, as it mentioned in German, is about 30 degrees. And if you combine these two, you see that you have an area efficiency F of about 35%. These are the relative irradiance losses, and you have here this shadowing angle. Let's go back to the example again, 14.1 degrees, elevation angle of our receiver 30 degrees here, and here we have losses in the vicinity of 5%. So that's it. Thank you very much. At the next lecture, we will discuss the solar concentration and solar thermal conversion. Thank you very much.